When we talk about ordinary arithmetic, we define the powers of numbers. Like we define 2 cubed, for example, 2 to the power 3, to mean 2 times 2 times 2. And there are some other cases in this definition as well, like you would define 2 to the 0 to be 1, and you would define 2 to the minus 3 to be 2 to the minus 1 times 2 to the minus 1 times 2 to the minus 1. We're going to do a similar thing for permutations in this video. So here is the formal definition of a power of a permutation, but all it does is exactly what I did for powers of 2 on the previous slide. If you've got a permutation S, and if you've got an integer m, so positive or negative, then we define s to the power m to mean, well, what it means depends on whether m is positive or 0 or negative. If m is positive, then we define s to the power m to be s composed with s composed with s composed with s m times. If m is 0, we define s to the power 0 to be the identity permutation. And on the other hand, if s is negative, if m is negative, we define s to the power m to be s to the minus 1, the inverse of s, times the inverse of s, times the inverse of s, minus m times. So let's just look at a quick example of this. Let's say we take s to be the permutation, which is the 4 cycle 1, 2, 3, 4. We'll look at some powers of this permutation here. So what would s squared be? S squared is, by definition, s times s, so s composed with s. So for example, s of 1 would be s of 2, which is 3. So if you think about what's going on here, if we do s twice, well, doing s once takes 1 to 2, so doing it twice takes 1 to 3. Okay, so s of 2 would be s of 2 would be 3, so s of 2 would be s of 3, which is 4. s of 3 would be 1, and s of 4 would be s of 1, which is 2. Okay, so actually we can find that the disjoint cycle decomposition for s squared from that, it is the cycle 1, 3 multiplied by the cycle 2, 4. Okay, let's do another one. So let's work out s cubed. So if you look at s cubed, well, let's think what would happen. So we'll start off with 1. If I do s 3 times, then 1 goes all the way to 4. If I do s 3 times to 4, well, if we do it once, we get to 1. If we do it twice, we go to 2. 3 times, we go to 3. And s cubed of 3 would be 2, and then we'd be back to 1 again. So s cubed is actually another 4 cycle. It's the 4 cycle 1, 4, 3, 2. Let's do another s to the 4. Okay, well this time if you do s 4 times, then 1 will go to 2, to 3, to 4, and then all the way back to 1 again. And 2 will go to 3, to 4, to 1, and then back to 2 again. So actually what's going to happen there is s to the 4 is going to be the identity permutation. And finally, well, let's look at the inverse. Let's look at some negative powers of s. S inverse, you know how to find the inverse of a cycle. You just write the things in the cycle backwards. So s inverse would be 4, 3, 2, 1. And if we wanted s to the minus 2, then the definition, the third case of this definition would say that was s to the minus 1 times s to the minus 1. Okay, so you can multiply that out if you like, and you'll find that what you get is 1, 3, 2, 4, like this. So actually this was the same as s squared. And if you look at s to the minus 1, you'll notice that this is actually the same as s cubed. So they may not look the same, but remember there are lots of different ways, in fact 4 different ways to write a 4 cycle, because you can start wherever you like. So thinking about that, you'll see that s cubed and s to the minus 1 are the same. They both send 4 to 3, 3 to 2, 2 to 1, and 1 to 4. So they really are the same. Alright, so there are some examples of finding powers of permutations. One of the useful things about powers in ordinary algebra is they obey certain rules, which you commonly call the exponent laws. Like if I multiply 2 to the power 7 and 2 to the power 9. Well, I don't know what that is, but it is 2 to the power 16 for sure, 2 to the power 7 plus 9. And if I do 2 to the power 4, all raised to the power 3, then the result of that is 2 to the power 12, which is 2048. No, it's not. 4096. Okay, so the same laws apply for permutations. So if you have any permutation S and any integers a and b, so positive or negative, then it's always true that s to the power a plus b is equal to s to the a times s to the b, and s to the power a, all raised to the power b, is equal to s to the power a times b. So this is, again, occasionally useful for doing calculations with powers of permutations. So let's stick to our permutation S being the same thing that it was on the last slide, the 4-cycle 1, 2, 3, 4. Let's look at how these exponent laws might help us do some calculations. So for example, if you wanted to know s to the minus 1 times s to the power 3, well, okay, you know now that that is s to the power minus 1 plus 3. So that is s to the power 2, and we worked that out. That was the 2-cycle 1, 3 multiplied by the 2-cycle 2, 4. Okay, another example. What if somebody asked you for s to the power 101? So you don't want to be working out the 101th power of something, because there's a lot of work to be done there. So we could make an observation here that we noticed before that s to the power 4 was just the identity permutation. So if we had a multiple of 4, let's have a simpler thing. What if we had like s to the power 16? That's s to the power 4 times 4. So that's s to the 4 to the 4. Okay, but we saw that s to the 4 was the identity. So what you've got there is the identity to the power 4. And you know when you compose the identity with itself, you just get the identity again. So this will be the identity. So 101 is not a multiple of 4. But we could just look at what is, what's the biggest multiple of 4 that we can fit inside 101? Well, it is 4 times 25 plus 1. Okay, now we can use some exponent laws in our favor to make this easier. So we could write this as, this is s to the power something plus something. So we can write it as s to the power 4 times 25 times s. Alright, and now I can use the other exponent law on s to the power 4 times 25. That's s to the 4 all to the power 25 times s. Okay, as we just said, s to the 4 is the identity. So what you've got there is the identity to some power times s, and of course composing the identity with itself however many times, you always get the identity. So this is just the identity times s. Let's put the composition symbol in there just to make it a bit clearer. And the identity composed with s, you know that composing with the identity doesn't do anything. So you've just got s again. So these exponent laws can be kind of handy, can be useful when you want to compute powers of permutations, because they can save you a lot of effort. Alright, so our permutation s had this nice property that s to the 4 was the identity. And we're going to generalize this by saying that the order of a permutation sigma, which we write like this, is defined to be the smallest strictly positive number n, such that sigma to the power n is equal to the identity. So for our recurring example, s was 1, 2, 3, 4, then 4 really was the smallest strictly positive power of s equal to the identity, because s to the power 1, which is s, is not equal to the identity. S squared was equal to 1, 2, 3, 4, and that's not the identity permutation. S cubed was equal to 1, 4, 3, 2, or 4, 3, 2, 1 if you like. And again, it's not the identity, but s to the 4 was the identity. So the order of s was equal to 4. It was the smallest power, which was the identity. Okay, let's try another one. What if we took t to be equal to a 2-cycle? Let's say 1, 2. Okay, well t to the power 1 is t, which is not the identity. But if you work out t squared, you'll see that that is the identity. So the order of t is 2. Okay, one further example. Let's try an example which isn't a cycle. So if you take, for example, what's the next letter? U. U to be, let's say, 1, 2, 3, 4, 5. Now, I'm not going to work out the powers here, but you can check that u to the power 1, that's u, it's not the identity. U squared isn't the identity. U cubed isn't the identity. U to the 4 isn't the identity. U to the 5 isn't the identity. But u to the 6 is the identity. So it turns out, when you do enough calculations, you'll find that the order of u is equal to 6. Okay, we're able to give a general formula for the order of an M cycle, which I've written in the middle of the slide here. So what I'm claiming is that the order of an M cycle, any M cycle, is equal to M. So let's give a proof of this result. A proof of this result about the order of an M cycle. So if I want to prove this, then what I've got to show is that the smallest strictly positive power of this M cycle, which gets you back to the identity, is the mth power. So I need to show two things: that all of the powers up to M are not the identity, but the mth power is the identity. So let's have some notation. We're going to let A be equal to A0, A1, up to AM minus 1. So an M cycle like this. So we have to show that the first m minus 1 powers, so let's say a to the power I for I between 1 and m, is not the identity, but a to the m is the identity. Okay, so that's not too difficult to do, because you can just, if you want to show something's not the identity, you just have to show that there is some number which it doesn't send to itself. And it's easy to find such a number, because if you have that I is between 1 and m, then think what happens when you do a to the power I to a0. So doing a once sends a0 to a1. So doing it twice sends a0 to a1 and then to a2. Doing it 3 times sends it to a3, and doing it I times will send it to ai. And of course, in cycle notation, all of the numbers a0, a1 up to am minus 1 must be different. So this is not the same as a0. So a to the power I is not the identity, because it sends a number a0 to something which wasn't a0. So we've done the first thing that we needed to do, and now we need to show that a to the power m is the identity. But of course the same kind of argument works, right? I mean, if you do a m times, well, think about what would happen to a0. If you did a m minus 1 times to a0, you'd end up all the way at the end of the cycle at a m minus 1. And then if you did it one more times, then you'd go back to the start and you'd be back at a0 again. So let's just generalize that for any, let's say, j between 0 and m minus 1 inclusive, then you have a to the m of aj is, I'm going to use my exponent laws. I'm going to do a to the j times a to the m minus j times aj. Okay, so what happens in that inner bracket? What happens here when I do a m minus j times to aj? Well, if I do it m minus 1 times, m minus j minus 1 times, I'll end up at the end of the cycle at am minus 1. If I do it one more time, then I'll be back at a0. So this will be a to the j of a0, which, as we've already seen, is just aj again. Okay, so a to the m sends each aj to itself. So a to the m is the identity permutation. Alright, so we've proved that the order of an M cycle is M.